So we're going to look at these notes today, which should be pretty simple, straightforward. As far as math or anything, the concepts might be a little confusing. I'm going to try to go through them in the order that makes things the easiest. So I know that the order I've set it up is going to give you questions as we go through it. I'll try to address them as they come up. So let's just go to it. So today's notes are on color and reflection. So, as the story goes, back in 1666, Newton did the first scientific experiments to produce color from white light by passing a beam of white light through a prism, so light from the sun. And the colors fell out in order from violet to red, which he called a spectrum. Now, because he's credited with first studying the spectrum, he's obviously not the first one to see it. But he's the first one to, take some measurements, write things down. So these are the colors that come out in the spectrum. So when I say he was the first one to do experiments, like I said, he didn't invent the color red or decide to call it red. It was already there. He just, took stuff and he took some measurements. So what measurements might you ask? Well, one of the things he did was he measured the colors. He measured the temperature of each color. So for example, he put like a thermometer into the color spectrum. And he found that, obviously it got warmer than the room around it. But certain colors made the liquid in the thermometer measure hotter. So it turns out that, when he moved it around, it seemed that it was coolest in the violet/blue part of the spectrum, but then as he moved to the red end of the spectrum, his thermometer recorded that it was slightly warmer. And what's interesting about this is one of the experiments he did is he did something real crazy. He noticed that it was red near the end of the spectrum, and so as he kind of got near the edge, it got warmer and warmer, and actually it was warmest just outside where he could see, which is weird. Because he's got a thermometer and he's measuring the colors of the spectrum, and it's getting warmer as he's going further and further into the red. And then when he gets just outside the red, where there doesn't appear to be any light at all, it's the hottest. Indicating that there was something there that he could not actually see. That's the beginning of the infrared part of the spectrum. Now, I'm not going to go into too much detail here, but part of the reason, I'm not saying that the red part of the spectrum is warmer than the violet part. What I'm saying is the red part of the spectrum for his thermometer was able to heat it up more effectively, right? If his thermometer had been something like water, light, the red end of the spectrum gets absorbed by water easier than the violet or blue end, which is why water is blue, because as the light strikes it, the light on the top, stuff that gets absorbed first is like the red end of the spectrum, like the infrared and the red gets absorbed, leaving the colors that you see, right, the blues and the greens. So it gives it that sort of cyan color. But as you go deeper and deeper into the water, it will start to absorb not just the red, but then the greens, and then eventually the blue and the violet, leaving nothing. So if you get on far enough, in, say the ocean, it's just black, right? Because eventually the water will absorb all of those colors. It's just more effective at absorbing those longer wavelengths first. So now you'll notice these are the colors of the spectrum: red, orange, yellow, green, blue, violet. I know for some reason you guys are still taught indigo, probably. I got news for you. Indigo is not a color. A lot of people get offended when I say that, but here's the deal. For all you indigo apologists out there, Newton called these things, red, orange, yellow, green, blue, violet in this order. He's the one that stuck indigo in there. he stuck it in there so that there would be 7 colors instead of 6. Why 7? Because he wanted it to have the same number of colors as the notes you have in Western music. Do, re, mi, fa, sol, la, ti. That's literally like why he wanted indigo in there. It's not, scientifically today, indigo's not a color, so I'm sorry. So Roy G. Biv, are the colors always in this order? Yes, in a spectrum, yes. Because each color has a unique wavelength, and each wavelength bends differently due to slightly different wavelengths. And so this makes sense. And so this goes into refraction, which we're not going to get too much into today, but essentially the reason why, it goes into, say, a prism or glass, and it comes out in this order is just think about, cars traveling down the highway. Let's assume you have a very large, say, like red 18-wheel truck, like Big Mac truck, like from the movie Cars. And then you can imagine like a small violet car, like a smart car. If they're both traveling down the highway, can they both drive 60 miles per hour? Yeah, they could. And if they did that, they would be like right next to each other, right? But let's say that there's a turn up ahead where they have to turn 90 degrees. Which one's going to be able to turn the fastest? The little smart car or the big 18-wheel truck? Smart car. So as a result, the shorter wavelengths bend more than the longer wavelengths because they're longer. Does that make sense? Like the 18-wheel truck is going the same speed as the smart car. It should not turn at the same rate as the smart car, okay? And so hopefully that makes some sense why it always comes out in that order, because violet is the shortest, red's the longest, and everything else is in between. So here, I guess, let's just send there to sit. These things do link to some videos, which I'm not going to play right now. So here's a question. So as to what color are your eyes the most sensitive?
That like neon yellow thing he talks about in the car truck.
Yeah, it's the yellow-green, the chartreuse color. That's again the color your eyes most sensitive because it's in the middle of the visible spectrum. You can see what this is trying to show me. So yeah, chartreuse. Okay. So why is the sky blue? This video goes into detail to explain it, but essentially, and I may have explained it in here already. First of all, the sun produces white light, and that white light strikes the atmosphere, and our atmosphere is mostly made of oxygen and nitrogen, and molecular oxygen, nitrogen, N2O2. They're basically the same size, and when the light comes in, it absorbs violet the most and blue light second most of what we can see, and it scatters those. So it scatters violet the most and scatters blue the second most. As a result, essentially light coming from the sun, let's say it was going to strike a piece of sky over to your left, hits that, gets scattered, which means it goes in all directions. If you have to look at that sky that's over to your left, you'll see blue coming from it. Now again, it's very faint, and so you need a lot of sky to see it. But again, the sky is about as blue as, say, the water. If you want to get technical, we say things have colors because of what they reflect, not because of what they absorb or scatter. So I'm not going to get into too much semantics on that. But essentially, that's why the sky is blue. But if you take the blue light out of the white that the sun produces, well, then that leaves a few colors left. Now, if you're talking about the full spectrum, well, you got yellow, green, red, orange, all that stuff. But as the sun gets lower in the sky, the light from the sun has to pass through more atmosphere, and therefore the other colors do start to get scattered. The green will scatter off, and then the orange, and then leaving the red at the end. And so the beginning and the end of the day, you might notice that the sky really isn't blue; it's more like red. That's all the sun has, that's all the light has left, because that's go through so much atmosphere. And I think it's really neat when you start to think about it, because the colors of the sky change, based on the sun's position, but literally, like, if you think about it, we're here in Denton. and you have the light from the sun, striking here and down. It's not quite overhead, but it's getting pretty close. But you can imagine, in another part of the world, like the sun is rising or setting right now, right? But think about this, if the sun is rising or setting, what's happening is essentially you're seeing light striking the Earth's atmosphere here, turning the sky blue, but some of that light from the sun is passing right by us and going way over to the other side of the planet where they're seeing the sun rise or set. And so that red light that's not getting scattered out here is making it all the way over to the other side, right? And so what's interesting is that, this happens because the Earth is curved, because it's spherical. And what's interesting about it is that even though there's people that can be thousands of miles away from you, we're essentially looking at the same sun at the same time, but they're seeing this light a few fractions of a second later, and it's the same light that just passed by. And again, that video goes into that detail, but here's some good drawings. So this is a question here. It says, well, if violet scatter the most, why doesn't the sky appear violet? Because human eyes are just not very sensitive to violet. Human eyes are basically sensitive to three colors. We call them the primary colors of light. What are those three colors? Red, green, and blue. Hang on. So this is the issue. Because when we talk about colors, there's confusion. Because with light, there are three primary colors. The primary colors of light are red, green, and blue. But we can't confuse those with the primary colors of pigment or paint. Those primary colors are cyan, magenta, and yellow. And for some reason, when you're taught paint in elementary school, they don't call them cyan, magenta, and yellow. They call them blue, red, and yellow.
Red, yellow, blue.
But they're not that color. I don't understand. But we're gonna get into that detail today, so that'll make some sense because they're very much related. And here, I kind of already talked about this. Why is the ocean cyan again? It essentially absorbs red first, and then so on and so forth. So here, this video, shows a guy jumping the ocean with like a red apple, and he swims around with it. You see it change color? I know. So speed of light. So we've talked about this before. We know it's about 3 times 10 to the 8th. Galileo was the first to hypothesize that the speed of light is finite. Essentially, before Galileo, everybody was just like, it's infinite. And he was like, yeah, it's probably infinite. But his experiments led him to conclude that light is too fast to measure. It says too fast to measure. It really should say too fast for him to measure. He just knew that, trying to use like an hourglass, like saying goes in out, that's just not the most accurate timing device. And he was aware of that. Ole Romer was a Danish astronomer, made careful observations of Jupiter's moon Io over 6 years. What's interesting about the Galilean moons, like the 4 largest moons of Jupiter, is even with a mildly powerful telescope or binoculars, you can see the Galilean moons. And they're very, very obvious because they're very large. And so what's interesting here is he looked at Io, which is just one of the craziest looking moons you're ever going to see. And he watched it over the course of 6 years. And basically, you can watch, the moons go around Jupiter. You go look at them every day. And what he noticed was he could start to predict, the exact second that Io would come out from behind Jupiter. But what he noticed is that he could actually, because it's so far away, he could actually predict, it should show up now, but I can't see it yet because the light hasn't gotten here. Does that make sense? And so he was the first to calculate the Earth's orbit diameter. So, how far from one side of our orbit to the other. And he concluded that it takes light about 22 minutes to travel this distance. okay? So this proved that light has a finite speed, and light can circle the globe 7.5 times in 1 second. It's one of those things to be like, oh yeah, it's 300,000 meters per second. But when you start to get down to it, you know, light in 1 nanosecond, 1/1000th of a second, 1 nanosecond, light can travel almost a foot. It's like 11.25 inches. That's not much distance, but 1/1000th of a second is not much time. In 1 second, you could circle the globe 7.5 times if you're traveling at speed of light. Like that's incredibly fast. It's hard to understand what's going on. So here, American physicist Michelson measured the time it actually took for light to travel between 2 mountains. He's credited as the first person to actually measure the speed of light back in the day. Essentially, I'm not going to go through the whole experiment, but essentially light, you know, they lit a candle like next to them. You put like a mirror on a mountain 35 kilometers away, and then used a telescope to look at the candle next to them and measured the speed of light, basically how long it took for him to notice the candle was lit. He was the first American ever to receive the Nobel Prize in Science for his work. In 1983, we defined the speed of light in a vacuum, C, to be 299,792,458 meters per second. All right. But again, we pretty much just round that. Again, it's not exactly 3 times 10 to 8. All right. So when it comes to light, there's 2 basic categories. There's luminous bodies and illuminated bodies. So luminous bodies are things that emit light, and illuminated bodies are things that reflect light. So that's it. We got 2 categories. However, it should be noted that a lot of things are luminous. For example, you guys create your own light. However, is it in the visible part of the spectrum? No. And so generally, these terms are just reserved for things that we can see, right? Because again, who cares if it's making light that you can't see, because you can't see it. So there's a couple of definitions here. We're not going to get too bogged down into this stuff for the light, but I wanted to define them because they're used in the real world. We have illuminance. It's the rate at which light falls on a surface. And so that's measured in lumens per square meter. And so what's a lumen? Well, that's our measurement of luminous flux. It's the rate at which light is emitted from the source. So lumens is our way of measuring, essentially, you kind of think of like photons coming out per second, like how much light is coming out. That's lumens, and then, you know, a luminance is lumens per square meter. Luminance is essentially, you know, if you go to buy a light, you know, I'm going to buy this lamp, I'm going to buy this bulb, whatever, they'll give you usually the illuminance of the bulb. But again, illuminance depends on the distance, because, you know, you can have a 100-watt light bulb right in your face, it's pretty bright. But if it's in your ceiling and you have 40-foot ceilings, that's probably not bright enough. And so, you know, it just kind of depends on, you know, the area that it's going to be covered, which again, for most lights, it kind of depends on how far away you are. Speaking of how far away you are, this brings us to the inverse square law. This is why we define illuminance as per square meter, because as light spreads out from the source, it spreads out in all directions. So you can think of it like light falling on the area of a sphere. And so if you think about something like, say, the sun that's just there out in space, it shoots out light in all directions, roughly the same amount in all directions, up, down, left, right. And the Earth really only receives a very tiny fraction of the light that the sun puts out. And you can imagine, you know, this, if you think about in terms of like just straight up photons coming out, well, if you have an area that's really close to it, it's going to capture a bunch of photons. Well, if you move that same area back, let's say 3 times as far, then that one particular area is not going to capture nearly the same amount of light. And so this is the inverse square law. It's not the first time you've ever seen it. Okay? You've seen the inverse square law, like for instance, when you studied electricity with Coulomb's law. It's, the force between two electric charges is, K times electric charge 1, electric charge 2 over the distance squared. Or with Newton's law of universal gravitation, it's, the force between two bodies is the universal gravitational constant times m1, m2 over the distance squared. So inverse squared is a thing that you guys have seen a lot, and it's not going away anytime soon, but I like to study it a little bit when we get to light, simply because you can't really see gravity, you can't really see electric force, you can't see magnetic force, but you can see light. And we can easily, move, have a light bulb and move stuff away and see, oh, okay, it gets dim, right? You guys know that, right? You have a flashlight, you turn it on, shine it right in your eye, it's kind of bright. But, if you back up from it, it's not too bad. And so specifically, the area that's covered, if you double, let's say, the distance you go away, you don't double the area the light covers, you get 4 times the area. Because, like it's covering a sphere. So if you move it back, twice the distance, you get 4 times more area. Or triple the distance 9 times, so on and so forth. We have these two terms, which are pretty, hopefully you guys know what these terms mean, but transparent, translucent, and opaque. So transparent, light passes through it. Translucent, light kind of passes through it. And then opaque, light does not pass through it. And so again, we typically use these terms when we talk about visible light. All right, colors of light. So white light can be formed by mixing the 3 primary frequencies of red, blue, and green. We call this color by addition. When we do this here, you should note that if you shine, blue light and red light, where they overlap, you get magenta. We call that a secondary color of light. Green and red overlap, they make yellow. And then blue and green overlap, we call that cyan.
You get yellow from
Well, that's just what it means. So, I was going to wait to do this demo, but we can do it now. I was just going to wait because I'm recording and it's not going to show up on the recording. So if we plug this guy in here, so this has 3 LEDs. Turn these on, but not very bright. Because these LEDs can be quite bright. Stop. All right, so y'all should be able to see. There are 3 LEDs in there. Now see that? What colors are they? Blue, red, and green. Okay, so I'm going to turn them all off now.
I couldn't.
So, red. I wanted to show you what was inside because you're going to see. So I got red, I got green, I got blue. So blue and green. Cyan. So green and red.
That's not yellow. Okay, color one, man.
And then red and blue give us magenta, and then all 3 gives us white. So white, red, green, blue. Is that better? Again, the further I get away, the more light gets spread out. Inverse square.
That's crazy. Can I have that? How much was that?
Not very much. There you go, you can have it. But again, it's kind of plugged in, so I can't really pass it around the room. what I want you guys to realize is that this really happens. And so it's funny to put this on here because literally the projector is only making red, green, and blue. And so by making the other colors, I'm proving that you can make all of the colors, but you can't see it doing that, you know? And so it becomes this whole thing of like, well, it's not really doing that. It's like, but that's how it works. Like, that's the only way it works. So now, when we're talking about human perception of colors and stuff, we have to understand that what we see is based on, well, our biology. And inside of your eyeball, you have rods and cones. Like, these are the cells that detect light. Rods detect basically shades of light and dark. And they don't need as much light to be activated. So if it's very dark, pretty much only your rods are working. There's only one type of rod, and so there is no color differentiation when your rods are being activated. It can do like shades of gray essentially, but it can't show you colors. That's what the cones are. And your cones, in your eyeball, you have 3 different types of cones. You've got red cones, blue cones, and green cones. Yeah, some people they don't work. But that's where you get colorblind from. There's different types of colorblind. You'll notice that there's 4 different types of colorblind. Essentially because you can have one of those 3 cones not working or not there. And so that leads to different types of vision. But also, you could have, say, 2 of them not working or all 3 not working. If all 3 don't work, then you truly are colorblind and you just see gray. So what's interesting here is that you can see all of these different things, but this is primary colors of light. They're not primary colors of paint. And we have not fully explained why we see what we can see. We'll get to that shortly. But this is like essentially if you have a light, think about that demo I just did for you. I'm shining this color plus this color, right? Or like your phone, your tablet, or whatever. It's essentially just shining those 3. Now, I will put a caveat in here. Most of our technology, especially LEDs, are not very good at creating one of these 3 colors. The one it's not very good at creating is actually green. As a result, and the thing is our eyes are most sensitive to green, and so it's probably not so much a lack of our technology, but we're just used to seeing more green because of the light from the sun. And so as a result, when we make displays that put out just as much red, blue, and green, it doesn't look right to our eyes. So as a result, most displays, if you're talking about like a pixel, most displays will have a red pixel there, a blue one, but actually 2 green pixels to put out enough light for what our eyes expect. So that's just a little side note there, that if you actually go, with a magnifying glass up on your device, you might be like, there's way more greens here. Yeah, that happens. And so we have what are called complementary colors. Complementary colors are 2 colors that make white. So the complementary colors are a color, like a primary plus a secondary, so like red, and then if you look across, like the opposite would be cyan, right? Like blue and yellow. Because essentially yellow is green and red, so if you already have green and red with yellow, well, you just need one more to make white, right? Now, that's actually what your lab is on today, is just taking essentially a light bulb, quote unquote, it's a virtual lab, and you're going to make the different colors. And so one of the things you're trying to prove is the fact that you can just kind of mess with these 3 colors and make any color you want. All right? So here's the primary colors of pigment. Primary colors, or pigment, is formed by absorption rather than emission. As a result, the colors of light are done by addition, right? You do red plus blue. Red plus blue plus green, right? That equals white. With pigment, it's colored by subtraction. It's taking away light. Now, when we start talking about pigment, think about just white light coming in at first. So here on the screen, you can imagine, okay, let's say it's white, completely white. Then I get some paint and I come up here and I paint cyan. Okay, what is happening to this white light that's coming in physically? Well, what's happening is white light's coming in. Let's assume that it's only the 3 colors we can see. If it's just the 3 colors we can see, then all 3 would hit the white screen and reflect out to your eye, you see black. But if it's just, if I painted it cyan, what happens here is all 3 colors come in and it absorbs one of those. Which one does cyan absorb? Red. Cyan absorbs red, leaving which 2 to reflect to your eye? Yellow and green. Not yellow and green. Blue and green. Because it's absorbed red. So that's, do you all see how this color by subtraction? So now even if I had the full spectrum here, like let's say the sunlight shines down on your cyan shirt, well, it's essentially only going to be able to reflect, wavelengths of around this color. So it could straight up be reflecting that light blue color to you, or it could be, reflecting blue and green. But essentially your eyes can only see red, green, and blue, so that's kind of what we focus on. But then you can imagine I come in here and I paint part of the screen with magenta. Well, what does magenta absorb? Green. And so you should notice that if I overlap the cyan and magenta, well, cyan takes away red, then magenta takes away green, what's left? Blue. And then if I paint theoretically all 3, I get black. Now, I know for you guys, especially in practice, like if you've ever painted something and your art teacher told you can make black by combining them, you just start squirting a bunch of stuff together and it just comes out nasty brown or whatever. Again, it's just like the light, it has to be in equal proportions, right? You can't just have, but a bunch of yellow, but like barely any cyan. Be like, oh, well, that should be, black now. It's like, well, you got to have the right proportions, right? That's 90%, I'd say, of painting is just dealing with the colors and mixing them to make the colors that you want. But see, now, hopefully you guys kind of understand colors, of light and colors of paint, and those 2 things together are what make our perception of the world. And what's really interesting is that if you don't start with white light, you don't necessarily get the correct, reflection out that you want. And that's actually one of the big things. A lot of our street lights are not white. They're not like sunlight. Most of them are kind of dingy yellow because they're sodium vapor. And as a result, it's kind of yellowish. And so if somebody wears something that doesn't look right, say they wear more of a reddish or a bluish shirt under that light, what ends up happening is it absorbs colors and reflects them differently, and you can see different things just based on the color of light that I'm shining. Does that make sense?
It does make me sure. So, like physically, when I use paint, if I mix red and green, I'm getting like brown, something like that, right? But if I use white, I get yellow. If I use white.
Okay, you could do that, but what I'm saying here is that these are the 3 primary colors of paint. If you're mixing, what did you say?
Red and green.
Red and green, you should get yellow. If you're not getting yellow, then probably these are not, or sorry, if you're mixing red and green, yeah, that should not give you yellow. Magenta and cyan should give you yellow. But yellow is a primary color. I think I just misspoke on that. Yellow is a primary color, so you're not really going to be able to get it by mixing the paint. Do you see what I'm saying? And so, if you want to get a little bit deeper into pigment and dye, like, I know you guys are young, but you guys have heard of lead-based paint, right? And how it's like toxic and all this. Hopefully, y'all weren't eating it, but the whole deal is it's one of those things that like I grew up with. Everybody talked about lead-based paint, blah blah blah. Make sure it's not lead-based paint, whatever. I didn't understand why. I never really questioned it. People just said it, but then I started thinking about like why are so many people concerned? Why does every single house have lead-based paint? Like why is everything got lead in it? Like, isn't it like an additive to paint to make it have a color? And it is. And the reason why it was in every paint is because you have to understand how paint works, is that they make essentially white paint, and then you just dye it. Like when you go to the store to buy paint, they just take white paint and dye whatever color you want. But they have to make the paint white, and originally they used lead to make the paint white, which is why all paint had lead in it. Now I think they use like aluminum oxide or something to make it white. Theoretically, it's not toxic, right? I don't know, just don't eat it. But the whole point is that you start with white, then you can add, essentially different amounts of magenta, cyan, and yellow to get the blend of color that you want. Okay, reflection. This is pretty easy. So when waves reflect, when waves hit a boundary, they have a choice. They can reflect or transmit. So if you think about like light hitting glass, some of it will transmit through the glass, but some will still reflect, right? You can see your reflection when you look through a window, but it's going to be pretty faint. And so whenever a wave hits a boundary between two media, some of the energy of the wave passes through and some will reflect. How much is transmitted or reflected depends on how different the two media are. Basically, the more they differ, the more is reflected. So let's just say most walls are pretty different than the air. So as a result, most of the, not just light waves, but also like sound waves bounce off of these things. Here, this brings up a very salient point here at the bottom. It says transmitted waves will stay in phase and reflected waves will invert when going from less dense to more dense, or stay in phase when going from more dense to less dense. So that seems just like a little footnote there at the bottom, but it's going to be really important that you guys know that when we get a little deeper into light. Okay? Light is one of those few units that it has a lot of things that I don't think are terribly complicated, but when I start to ask you guys like questions on these, it's going to get real ugly real quick, because these questions that the College Board likes to ask tend to be very, very intense on not so much the calculations. The calculations are fine, but they're going to be real intense on the amount of knowledge that you need to solve. And light is one of those few sections that I can show you like a question that seems pretty simple. It's only like 1 sentence or 2 sentence question. But in order to get to the right answer, there has to be 3 or 4 concepts that you have to know very solidly. Otherwise, you have no hope of answering this question. And this is one of those concepts. And so again, transmitted waves always stay in phase. So the transmission goes straight through. And so that's what you're seeing here in this little picture on top. It shows less dense and more dense, but you see how like the crest goes in, but it stays a crest even when it goes through to the more dense medium. Does that make sense? So transmitted waves are always in phase. That's the number one thing. It's very easy, but don't forget it. Transmitted waves always stay in phase, because the second part is where it gets confusing. Reflected waves sometimes invert and sometimes don't. They'll stay in phase when you're going from more dense to less dense, and they'll invert otherwise. And so I like to think that most of the time, like when in doubt, it's going to stay in phase. Does that make sense? Like it's only going to be inverted when it goes from less dense to more dense, which kind of makes sense, because if it's more dense, you can think about like more molecules are pushing our wave. And when it goes to something less dense, well, the more molecules can shove the less molecules, right? Whereas if you have less molecules trying to shove the bigger molecules, well, they kind of shove back and it gets inverted. And so that's what you see here, going from less dense to more dense. So again, you see the transmission stays in phase in that picture, and then it reflects, like right there at the boundary, you see how it reflects, but it comes back as a trough. Right? And then the bottom, picture, moving picture, just shows that they stay in phase. And that's going to be very critical when we start talking about like light canceling itself out and causing these other reflections that we can see. So do you have any questions about this stuff down here at the bottom of the slide? Like, I don't think it's too hard, but when you start to stack stuff on top of it, it's just going to be like one of like 3 or 4 concepts that you got to like shuffle through in your mind. It can get kind of difficult. What color is a mirror? Yeah, essentially, you could say the true answer is that mirrors are kind of like a smart white. But a lot of people are just like, but no, it's kind of green. Like, yeah, okay, it's kind of green, fine. So when light reflects, there's essentially 2 ways it can reflect off of a surface. So again, we talked about color because if light comes in and hits a surface, some of it can get absorbed, right? And then what's left is there to reflect. So if you have a nice flat surface, you get a specular reflection. That's what mirrors do. They give you a specular reflection. Now you might see something like the marker board up here or your desk. They look nice and shiny. They sort of give a specular reflection, but more or less it's still diffuse. And diffuse happens, when the surface is rough, essentially. But again, does this marker board or your desk look very rough? Not really. But you have to think, what is rough to the size of light? Right? If you think about light being a photon or being a ball, if I throw a ball down at this floor right here, it's probably going to bounce in and out exactly like we think, right? If I throw a ball down, it bounces out at the same angle I threw it in at, right? It's very predictable. However, if this floor was just like a bunch of rocks, like gravel, and I throw a ball down at it, is it necessarily going to bounce out exactly the way I threw it in? Well, no, because the surface is no longer smooth. Does that make sense? But again, what is rough or smooth depends on the size of the object you're using, right? And light is very, very small, and so in order for it to be smooth, it has to be smooth at the size that light is, which is why most surfaces are going to give us a diffuse reflection rather than a specular reflection. Right? I will say this about mirrors here, because there'll be like a mirror in a restaurant or something, and I'll see like kids like acting like you can't see them in the mirror. Light goes in and it bounces out, same angle. If you can see them, they can see you. Always. Now, they might have their back to you or something, but if you can see them, they can see you. Like, that is 100% true. And it's one of those things that a lot of people kind of miss. And there's some things that you can do to make it harder for people to see, like if you're hiding in the bushes and looking at somebody, that can make it harder for people to see, right? But, theoretically, they could look through the leaves and bushes and see you, just like you're looking through the leaves and bushes to see them. So it's very important that you know that, because light doesn't care about what direction it's going. Here, this goes into more specular versus diffuse. You can see here, this is a up-close view of toilet paper and a hypodermic needle. Hypodermic needles look pretty smooth. They are pretty smooth. Toilet paper looks pretty smooth, not very smooth. Matter of fact, that's actually what most paper looks like in general. For those of you who don't know what paper is, it's essentially a tree that we ground up into pulp, laid that pulp out and put some glue on it. So it's actually crazy how rough paper is, but how smooth it feels. Like wait, what? Like, we didn't even try to make that flat. We just smoosh it. All right, it's flat now. That might be the end. Okay, so that's the end of the notes. We can show a couple of videos. I have a couple of demos. I'm going to stop recording here.